Calculating enthalpy and using it to find the mass. First thing we need to do is write down our formula that I want you all to memorize. This delta H here, you can put a small r there if you want, I'm not gonna, but this delta H just represents the total enthalpy change, but it's a total enthalpy change for the whole reaction. Whole reaction is equal to the number of moles multiplied by another delta H, but this delta H is a little bit different because, again, you can put an R here if you want, and it's for the, again, this is for the reaction, and this here is for the, a not symbol, okay? So it's the standard molar enthalpy. Again, if you're not very clear on the enthalpy change and the standard molar enthalpy, please look at my previous video representing enthalpy change in 4 different ways, so that you kind of understand what we're going to be doing here, because this here, you should already understand the fundamentals for this video. We're just going to be using it and applying it to some practice problems. So this, again, is for the standard molar enthalpy, but specifically for the reactant or product. Now, how do we solve this question using and implementing this formula? Well, it asks one mass in kilograms, so let's first find grams first. Of methanol must be combusted to generate this much energy. Well, it's in kilojoules, which is good because that is what we need for the energy, because energy is measured in kilojoules and joules. So is this value here, this numerical value, going to be for this whole reaction enthalpy change, or is it just going to be for the specific reactant or product? The answer is going to be for the whole reaction. Why? Because the question doesn't state that this numerical value of energy is per mole of a specific reactant or per mole for a specific product. It just in general states that it's going to generate this much thermal energy. So a big value like this, in general statement, we need to put it for the whole reaction. So I'm just going to write 5.39 times 10 to the 5 kilojoules, and it's going to equal our amount of moles. I also want you to remember that because this is combustion, it is an exothermic reaction, it has to be a negative value, because this is how much is being released, not being absorbed. It's being released. And again, this is going to be multiplying by our delta H R naught. What value is this one going to be? Well, if you have a look over here for our methanol, this here is our formula, and we can see over here that it's negative 726.1. This negative 726.1 is kilojoules per mole. That means for every mole of this methanol, again, it's being combusted, so it's releasing energy. How much energy is it releasing? It's releasing this much. It's releasing that much kilojoules of energy. That means that our standard molar enthalpy here is going to be that value. Again, it has to be negative because it's releasing energy. Negative 726.1 kilojoules per mole of the compound in question, and that would be methanol. Now, we eventually have to find our moles, because once we find moles, we can easily find out the mass, and then we can find that in terms of grams. And then from grams there, like I said in the beginning, find grams first, then we can find the kilograms. You can use that by using this formula, N is equal to M over M, but I don't really like using formulas when you don't have to. I just like to use factors and just canceling out units to find the unit that we want. And again, I'll be showing you that shortly. But right now, let's just isolate for moles. Well, right now, it's multiplying this value. How am I going to get rid of this so that the moles is alone? The opposite of multiply is divide, so I'm just going to divide by that same value. That way that they can cancel out. But if you do it on the right side of the equal sign, you need to do it on the left side of the equal sign. So I'm going to do that here. That's it. So now I end up getting my amount of moles is equal to this negative 5.39 times 10 to the 5 kilojoules divided by, I'm just going to give me some more space here. It's going to divide by our negative 726.1 kilojoules per mole. However, this looks a little bit messy. Technically everything is over 1, so this is technically over 1. So if there's a fractions and then there's a divide in between, you can just change it into multiplication. So let's write this out again here and change this into a multiplication so that this thing flips. So now we have moles on the top, and then we have this on the bottom is equal to joules. So sorry, is equal to the moles. And then again, diagonally, these units are the same. So this and this cancels out. So this cancels out. So I end up just getting this value here, negative 5.39 times 10 to the 5 times mole divided by this value. So I'm eventually going to be getting, you can use your calculator here, 742.32 moles. That's how much I have for moles. I'm just going to bring this over to here so that we can finish this off and find the amount of grams, and then eventually use that to find kilograms, and then we're done. So this 742.32 moles here, I need to multiply by a fraction. Remember, whenever you're in doubt, just multiply by a fraction. Technically this is all over 1 as well. What are we going to do? Well, I need to put my moles on the bottom here so that my moles can cancel out because I don't want it anymore. And then I can have my grams on the top because that's what I want. I want the mass. Well, this awfully looks like the molar mass because it is. So for every mole, how heavy is it? Well, what is the compound in question? It is methanol. So you just look for methanol over here. So you can see the formula, methanol, right over here. It's CH3OH. So you're just going to find the molar mass for the carbon. So there's one of it. So you multiply by 12.01 grams per mole. Find it on your periodic table. And then you do the same thing for the hydrogens. There's 4 of them, so you just do 4 times 1.01 grams per mole. And then there's 1 oxygen here, so it's 1 times 16 grams per mole. You add them all up together, and then you should end up getting a value of 32.05 grams per mole. So this mole cancels out, this mole cancels out. So what are you going to be left with? You're going to be getting 23,791.42 grams. And again, we're just going to change this into kilograms. So you just go back three spaces. So you just end up getting 23.791 kilograms. Okay, if you just want to do 2 decimal places, that's fine. Kilograms. This is your answer. We have a thermochem equation. Determine the standard molar enthalpy of combustion of propene. So obviously this here is the propene. How are we going to figure this out? Well, again, write out our formula. And once you have that in play, we have to figure out what are we looking for? The standard molar enthalpy of combustion. Well, standard molar enthalpy of propene here, we have to look for the certain amount of energy that is being released per mole. Okay, per mole. We know that this value here in our previous video, this one is represented as per mole. Okay, but as you can see, there is a 2 in front of the propene. This means that this must have been multiplied by 2, because if you were to divide this by 2 and divide this by 2, divide this by 2, divide this by 2, this would also have to be divided by 2. So what your actual value is not 4,116 kilojoules. It's actually going to be half of that. So we don't even really need to use this formula here. You just kind of look for your C3H6, and then you just have to find per mole of it. So for every mole of this C3H6, you end up getting this much kilojoules of energy released per mole. So that would just be 2,058 kilojoules that is being released. That's the standard molar enthalpy. There is no value that is given to us for the total reaction, the total enthalpy for this reaction. It's not listed there. The only thing that they give us is the thermochem equation, which literally has the standard molar enthalpy in it. And then the question is literally asking for that standard molar enthalpy. But remember, it's per mole. Molar is representing per mole of it, but we don't have per mole. The thermochem equation, after it's balanced it all out and it was given to us, gave us 2 moles of that. So you just have to divide by 2. That's how we ended up getting that value. Next, again, this was A. Now we're going to go look for B. What is the maximum amount of thermal energy available from the combustion of 5 grams of C3H6 or propene? Well, let's write this out so that we end up just getting our 5 grams. But our 5 grams here of this propene, I need to always change it into moles. So let me change it into moles right now. So for every mole, how many grams is it? How heavy is it? Well, you just look for C3H6 on your periodic table. So it'll just be 3 times 12.01 grams per mole plus 6 times 1.01 grams per mole. So what do you end up getting? 42.09 grams per mole. So this grams and this grams cancels out. So I end up just getting 5 divided by this value. So I'm just getting 5 divided by the value gets me 0.11879. Moles. So now I have the amount of moles. But what is the maximum amount of thermal energy? Okay? You see how it's saying the maximum amount. This is the whole reaction, the total reaction. So right now, we are trying to find this value here, the delta H, the one that we didn't have in the beginning. So now it all makes sense why it's written in this question. We're trying to find this delta H. So again, I'm just going to put delta H is equal to our amount of moles, which is 0.11879 moles. And I need to multiply it by their standard molar enthalpy. Well, we've already figured out what the standard molar enthalpy is. It's this much energy released per mole of that. So I'm just going to be putting, again, this is released, so I can change this into a negative because it's an exothermic reaction. So negative 2058 kilojoules per mole. And then, of course, this is technically over 1, cancels out diagonally. I end up getting delta H is equal to the product of that times that. I end up getting negative 244.48 kilojoules. That's the answer. What mass of butane C4H10 must undergo complete combustion to produce 1 megajoule? So we can just change this megajoule into 1000 kilojoules of heat according to the following equation. So look at our thermochem equation. It's pretty obvious here. This is our standard molar enthalpy, so it's at the end. So this here is our standard molar enthalpy. There's only 1 mole of that C4H10, so this here is accurate. We don't need to divide it by anything. So this here is going to be our delta HR comb, right, the not symbol. So this here is negative 2877.6 kilojoules per mole of this C4H10. Okay, our butane. Now, what is our formula? This delta H, we can't forget. Is it written in the question? It is 1000 kilojoules, right, to produce this much general amount of energy according to the following equation. So this here, we can also write it as a given. It's 1000 kilojoules, all right? Remember, it is being released, so we can actually change this to a negative symbol, so it's negative 1000 kilojoules. So we end up trying to find our moles over here, which is fine, because once we find moles, the question is asking for mass. We can change the moles to mass at the very, very end. So let's finish off this question. So we have our delta H here, which is negative 1000 kilojoules of the whole reaction is equal to the amount of moles, don't know what it is, multiplied by our standard molar enthalpy, right, as written in the formula. So it's negative 2877.6 kilojoules per mole. There we have it. So all I need to do is isolate this, so divide this by negative 2877 kilojoules per mole. You do it on the right side, cancel it out. You do it on the left side as well, so I'll do it here too. So then I end up just getting my negative 1000 kilojoules multiplies, I just flip this over, moles over my negative 2877 kilojoules. So again, this is the moles here. So kilojoules cancels out. So you just get this times mole divided by that, end up getting a value of 0.34751 moles. So I'm just going to bring it over here. So this is how much moles I have. Multiply by a fraction, because technically this is over a fraction. Moles always on the bottom so that they can cancel out. How much grams? Well, look for C4, so you just do 4 times the 12.01 grams per mole of carbon on your periodic table, plus the 10 hydrogens times 1.01 grams per mole on your periodic table. You add them all up, you end up getting a number of 58.14 grams per mole. So this cancels out, this cancels out. What do you end up getting? The total value of 20.20 grams. That's the answer. I want you to try this next question on your own. Give it a try. It's a little bit of a longer one, so definitely try to be as disciplined as possible to get the correct answer. So pause the video, give this a try, let me know how you did. Alright, hopefully you've given it a try. Let's finish this off. We have our standard molar enthalpy is this value. So I'm just going to write down the givens that we have. So we have our combustions. Again, we can change this to combustion if you want. No big deal. Negative 2006 kilojoules per mole. Okay, that's what we have. Write the thermochem equation for the combustion of 1 mole of this compound to form carbon dioxide and water. So we have to create a balanced chemical equation, and then we need to figure out our delta H. Well, let's write this out. So we have our CH3, CH, OH, CH3, added with obviously oxygen, and it's going to be yielding certain products. Well, it's going to be H2O, as indicated in the question here, right? H2O, which is water. It's going to be vapor plus carbon dioxide. It's going to be vapor. You would actually have to balance this out. So hopefully you balanced that out appropriately. You just have to put a 2 over here, have to put a 9 over here, have to put a 6 over there, and an 8 in front of the H2O. So we're almost done making our thermochem equation. Right now we've done the balanced chem equation, but we need to eventually put our enthalpy value. Well, where are we going to put the enthalpy value? Are we going to be putting it on this side, on the reactants, or are we going to be putting it on the product side? Well, this is combustion, it's a release of energy, so it's pretty obvious that it has to be on the product side. Also, it's literally told us in the question that it's a negative value, so it needs to be over here. But remember, this is per mole. We don't have 1 mole. We actually have 2 moles of this compound, the propane 2O. So we actually have to multiply this value by 2. So it's eventually just going to be that negative 2006. So I'll just do it on my calculator here. Multiply by 2 gives you negative 4012. That's how you do it. Now, we could also divide this by 2, 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 so that we're only looking at just 1 mole of this CH3, CH, OH, CH3, 9 over 2, 4H2O, 3 CO2, and like our same value over here. Oops, sorry, this one should have been a plus. Kilojoules. Now, we've written out the thermochem equation for the combustion of 1 mole of this compound, right? 1 mole, this is a 1 over here. So we're done. So this is pretty much A. How much heat is given off when 25 grams of water is produced? So we're actually not going to be focusing on this propane 2O anymore. We're going to be focusing on the water. All right, so we have 25 grams of this water. Again, I don't want to be working in grams. I always want to be working in moles. So I'm just going to, again, technically this is over 1. Right, so we have 2 fractions here. Multiply by a fraction whenever you're in doubt. Put grams on the bottom. and moles on the top so that my grams can eventually cancel out. Well, in 1 mole of my water, right over here, you're just going to get 16 grams per mole plus 2 times 1.01 grams per mole. You end up getting 18.02 grams per mole. This cancels out, this cancels out. What am I end up getting? I just get 25 times 1 mole divided by 18.02. I'm going to be getting a number of 1.37. So 1.387 moles of my H2O. Now, this here is of my H2O. The thing is, we've done all of this in respect to the propane-2-ol. So we actually need to do a molar ratio and change this into our propane-2-ol. What do I mean by that? Well, I need to do a molar ratio by doing a certain amount of moles of H2O with a certain amount of moles of my propane-2-ol. So I'll just put my propane-2-ol over here, CH3, CHOH, CH3. Well, let's look at our thermochemical equation. For every 4 moles of H2O, there is 1 mole of propane-2-ol. So I'm going to be doing that. And this is how I'm going to be doing my ratio. My moles of H2O, my moles of H2O cancels out. I end up getting 0.34675 moles of my CH3CH OHCH3. Now I just need to put it into my formula of delta H. Again, this is for the whole reaction. I'm trying to figure out my whole reaction, right? It says how much heat is given off the whole reaction. So that's what I'm looking for here. Equal to my moles, which I've written over here, multiplied by the standard mole enthalpy of my propane-2-ol. And I already know that as indicated up here since the beginning of the question. I'm just going to multiply that over here. So let's plug in the values. So my delta H is what I'm looking for. My moles here is my 0.34675 moles. And I'm going to be multiplying it by my negative 2006 kilojoules per mole. So that my moles cancels out. I end up getting a sum value of negative 695.58 kilojoules. That's the answer. Alright, these are the 2 green questions of the day. Please try these on your own. Pause the video, give it your best shot, and then I'm going to be showing you the answers shortly. This is the answer for the first question. This is the answer for the second question.